Next speaker is Peter Walling from Baylor University.
The slight delay there was to readjust the computer because this is being simulcast to India. So I'll ask you not to hurl any obscenities at me at the end of this talk. My name is Dr. Peter Walling. I'm a clinical anesthesiologist. Ken Hicks is a biomedical engineer. Miguel is a mathematician. We like to look at brainwaves and their associated attractors. When I've spoken to residents about attractors, their eyes normally glaze over, so I'm just going to do a little recap for you. If you take a pendulum and look at its dynamics, the dynamics can be expressed by a dimensionless point traveling around in a circle. Every slight advance of that point represents a change in the balance of the forces associated with that particular dynamic. If the pendulum is perturbed, the circle develops a wobble, but the point is rapidly dragged back into line by the attractor, and that's why it's called an attractor. The attractor is scale-free. It does not have any size. It exists in a phase space or a mathematical space, and it has a dimension. So the attractor at the bottom here is one dimension, and it's a limit cycle attractor. Top left is the limit cycle attractor again, this time representing a sine wave. Sine waves are important in the study of consciousness because if that sine wave is modulated, if its amplitude is modulated, then the whole sinusoidal thing there becomes like an amplitude modulated signal, like an AM radio signal. So these modulations actually carry information, and of course this is reflected in the attractor itself. Once we get to the next attractor on the top right here, there's two changes. We'll move from the clock model now to the brain model. Imagine that trace is an isoelectric EEG and that a burst occurs on it. The attractor begins to be filled in. That is to say, it's not a one-dimensional circle anymore. It's beginning to be filled in. The curls on the spiral here are self-similar, and they have a fractal shape, and it's a fraction of a dimension, and that's why it's called a fractal. The one on the bottom left here is represented by another brainwave joining the first one. And this is now a periodic attractor for obvious reasons. Now the point and the periodic attractors exist on a phase plane. If an incommensurate frequency gets added to that, the phase plane will sometimes burst into phase space. And now the attractor exists in three-dimensional space, although this particular one is only 2.5 dimensions because it follows a complex two-dimensional plane like the glaze on a donut. The point, periodic, and torus attractors are important to students of consciousness because when they occur in a dissipative system like the brain, they are one of the classical pathways towards chaos. And Ken Hicks and I, a few years ago, described these very changes during anesthesia and during the emergence from anesthesia. Stage 4, top left, is a point attractor. This is very deep anesthesia, isoelectric with or without a point attractor. Stage 3 is a periodic attractor. This is the normal stage of surgical anesthesia, which we aim for during surgery. Right before the patient wakes up, the attractor turns into this toroidal shape, and this is associated with delirium, what used to be called the stage of delirium, but is right before you wake up. And then return of consciousness is this strange-looking thing at the bottom. Now, the transition from 3 to 2, from the periodic attractor to the toroidal attractor. We plotted it in a patient who was waking up very slowly. The little pink dots represent the attractor dimension measured every 3 seconds. The orange bars represent the level of the anesthetic in the bloodstream. And you can see that as the anesthetic diminishes gradually, there is a sudden, nonlinear, big increase from 1.5 periodic dimension to 2.5 dimensions, which is the toroidal attractor. This, incidentally, is extremely easy to see on an EEG if you're working out the attractor at the same time. We've created a program which generates the attractor at the same time as the time signal of the EEG. All you do is to turn it sideways. And then instead of seeing a straight line of the flat plane, it suddenly goes boop, like this as the patient is about to wake up. Now, moving on from anesthesia, we also took an interest in the emergence of consciousness through evolution. What we did, I live in a farm, that's why I could do it. We took animals and measured their EEG, measured the best attractor we could find, and plotted that against the time of their appearance in the fossil record. So already you can see that this is not a terribly accurate plot, but we weren't looking for proof, we're looking for clues. There are 21 species here, and I think the points to note related to our interest in consciousness is that, for a start, the animals more or less retain their evolutionary ranking. The one factor which seems to correlate with the increasing dimensions of the EEG attractor is the passage of time. And approximately 200 million years is required for each dimension. We were interested naturally to see where 3 dimensions occurred, because that was the dimension at which our patients woke up from surgery. And this occurs about the time of the amphibians. The animals with very low dimensions, that is 2 and below, fall foul of a law called the Poincaré-Bendixson theorem, which basically states that if you have a really simple attractor, just a circle, a bit like the pendulum, if you have a very simple attractor with a dimension of less than 2, that is incapable of representing complex dynamics. So we would suggest very tentatively that the clam and below, if you like, or probably not conscious. There's an indeterminate group of the fish. The octopus, ray, and aplysia, incidentally, I lifted from an article from the Scripps Institute in San Diego. Now, the human was multitasking, tapping her foot, listening to rock music, and reading Plato at the same time. And so she clocked up a dimension of just under 5. And we've always felt that this plot is really not a fair assessment of what's going on. And the reason is that we don't show all the other results, because what happens during evolution is not just that your attracted dimension gets bigger and bigger and bigger, it's your capacity to work at higher dimensions, which increases. So we just threw all our results together and threw caution to the wind, and this is what we get. Now, we were interested in what was going to happen instead of in a human that was multitasking. What about a human that is monotasking? This is a screenshot of a pilot study that I did. We have the frontal EEG, the motor cortex EEG, the facial EMG, and the strobe light. The attractor, by the way, is between the red line and the blue line. I hope you can see that. The subject was asked to sit, relax, at their own time, of their own volition, hit the button. And then when the flash went off, to pout as quickly as possible. We found that blinking the muscle activity tended to mess or, give us an interference on the forehead. Between the red and the blue line, we kept seeing this little burst. And what's happened is that obviously one has lost the high amplitude, low frequency component of the previous EEG, and it's probably some kind of a gamma burst. Here's the problem. It's only 100 milliseconds long. If we want to do some analysis on this, if we were downloading at 240 samples a second, we'd only have 24 points to play with. Even at 1,000 samples a second, we would only have 100 points. So we were recording this at 8,000 samples a second. The reason was that we're actually trying to get a good-looking attractor, but that's by the by. And now we have 800 data points for this 100 millisecond burst, and this is what we can now find out. For a start, we get a very good picture of the burst itself. It's obviously a gamma burst, but you can see that there is a very high frequency component to it, and we want to know what that is. Now, because we're sampling at 8,000 samples a second, when you do a frequency analysis, you only get half of that number. So our frequency analysis only will go out to 4,000 samples a second. And here's what we see. Normal kind of looking frequency stuff on the left, but it's about 1,600 hertz, sticking up like a sore thumb. There is this inclusion, and we need to know if that's physiological or whether it's an artifact. It does not look physiological to us. In our experience, we don't normally see an EEG burst way out there all by itself. On the other hand, it doesn't look like a harmonic from the mains either, because there are no other harmonics. So we went downstream a little bit and took another sample right after the flash, and it's disappeared. So that was obviously an artifact, probably caused by the capacitor in the flash gun. When we look at some frequency bands, the burst itself is in the middle of this plot. The most dramatic thing is a sudden decrease in the fast beta waves, the 20 to 30 hertz beta waves. There's also a slight increase in the power of the fast gamma waves, which are in the band of 60 to 180 hertz. We have enough points to get a power spectrum from it, and our maximum power was at 86 hertz for this burst. And we can measure the dimension of the attractor, which was 2. And I will point out that we don't normally measure attractors to 5 decimal places. We barely will call an attractor anything more than a quarter or a half, because these are estimates. But we still use 5 decimal places as a check on our files, because if the file has been corrupted, then we will never get the same result again. With the same file, you should get exactly the same result every time. This is a subject doing mental arithmetic. They're subtracting 15s from 500. The frontal EEG and the attractor is shown. The movie is 50 seconds long. The actual brain operation is 50 milliseconds. So this is slowed down 1,000 times. And you can only do that if you're downloading very rapidly. And we were downloading, in this case, at 40,000 samples a second. And I would put it to you that you can probably get more information from that attractor than you can from the 4.5 brainwaves which it is representing. This posed another question to us, and that was, how much of that EEG should I use to actually make the attractor? So what we did was we took a sample from the inside of that file from 3 to 3.5 seconds when the mental arithmetic was well underway. This is incidentally is 500 milliseconds of EEG recorded at 40,000 samples a second. And you can see the very, very nice detail you get of the EEG itself. And what we decided to do was to say, well, look, if you measure the attractor of the first 2 brain waves there, you're just going to get a circle, and you're going to get an answer of about 1. and that's not going to be representative. So what we did that, and then we added 25 milliseconds at a time. So we go 25 milliseconds, 50, 75, to see how long it takes for this attractor to blossom out, expecting it to plateau out after a certain time when it was fully formed. And it seems that it forms, in this case, in about 400 milliseconds. To sum up, we sometimes record very rapidly. We don't always. I mean, it produces humongous data files, but we do, at our discretion, record very rapidly sometimes so that we can get more data for our calculations. It means we can analyze short segments of EEG. It means we can look at high-frequency components. It means that we can get a more detailed movie of the attractor. We can look for fleeting signs of attractors. For example, the trefoil is a signature of a torus attractor, like the Adobe logo. That's a trefoil. If you have an animal which is wiggling about, and you can just get a very short EEG run while the animal's keeping still, again, you may get enough for an analysis there. We can look for EMG and spindle activity, although we've really not found that a problem with humans. And we can plot the development of an attractor in 25 millisecond increments. And we ask ourselves, is this multi-dimensional attractor, which is in non-physical space, just like our perceptions, is this a good correlate for the dynamics of consciousness? Because more and more I've been asking myself, well, not how does my perceptual space get filled in, but where did that perceptual space come from in the first place? Thank you.